Okay, good. So I'm just going to give you a little update on Lucy, starting off with an overview. Um, as you all know, it's a tour of the Trojan asteroids. We're going to launch in October of this year, which is a little over 261 days from now. I'm going to show you the trajectory. Matter of fact, most of my talk is going to be centered around the trajectory. We do a main belt asteroid rehearsal of an asteroid we've named after the discovery of the Lucy fossil, Donald Johanson, in 2025. And we have 5 encounters with Trojan systems from 2027 to 2033 for a total of 7 objects. One was recently discovered to have a satellite. I'll talk a little bit about that. And then we have a near equal mass binary at the end, which is my favorite. So I'm going to start off just telling you about the trajectory, right? The whole goal here is to cover as much real estate as possible. These objects, Trojans, have a wide diversity in spectral characteristics. And one of the goals of Lucy is to understand that diversity. And in order to do that, we have to visit a wide range of objects, which is exactly what we're doing here. As I said, we launch in October onto a 1-year orbit. We do that so that we could have a small rocket. And we're going to use a series of Earth gravity assists to pump up the aphelion of Lucy's orbit until we get to the Trojans. So the first one is almost exactly a year after launch. That will put us into a 2-year orbit. Then we'll have another Earth gravity assist. That'll kick us out into Trojan storms. On the way out, we're going to pass this Donald Johanson main belt asteroid. By the way, it's a member of the Argonian family, so it's a really big object. That should be interesting. Then we're going out into the L4, and we're going to have 4 encounters, starting with Euripides. Euripides is a C-type. This is the one where we've recently discovered it has a satellite about 1 kilometer in size. You can see the orbital characteristics on my screen. And given that, we can actually get a density for Euripides of about 1. The biggest uncertainty is the size of the object itself. We're beginning to collect occultation data on it, so we should be able to constrain that a lot better. We've looked for satellites on all our targets. This is the only one where we found one, and maybe that's not surprising because Euripides is the largest member of the disruptive collisional family. And as we know, these kind of satellites often form in systems like that. Then we fly by the P-type Ptolemy. This is our smallest object. The Y's diameter for it is about 20 kilometers, so it's the smallest of the bunch. Then the spacecraft reaches aphelion and comes back in. Way back in, we go by Lucas. Lucas itself is a strange object. It's got a very long rotational period, 446 hours. We've got actually several high-resolution occultation experiments on it. I'm just showing you the highest resolution of the upper right by Mark Bowie. You can see it's an extremely elongated object too. So not exactly sure what causes this really slow rotation period or the shape. It'll be interesting to see this object. And then continue, we go past Orus. So just in the L4, we're going through past 2 D-types, a C-type and a P-type. Remember, diversity is the key. And then we're taking advantage of the idea, if you put an object with an aphelion near Jupiter and a perihelion near Earth, its orbital period is about 6 years. And therefore, we can use just the geometry to go first to the L4, then to the L5. We're also putting the spacecraft on an orbit. So its orbit is a multiple of the Earth's orbital period. And as a result, when we come back in, we're going to have the Earth available again to target our next object. Which is the Triglycemicia binary. It's a p-type. Two near equal mass objects, about 100 kilometers in diameter, on a circular orbit around one another. Right, they're tidally locked with a semi-major axis of around 680 kilometers. So this is, if you look out in the cold classical Kuiper belt, you see a lot of these things. So, this is probably the leftovers of a primordial system. So that'll be interesting to see too. All right, so this is a flyby mission, right? So, and we need to do flybys in order to cover the kind of real estate that we are, the diversity. But we're going to do every kind of measurement you can imagine. When you're flying by, it's somewhere between 6 and 9 kilometers a second. We're going to do surface geology. We're going to be able to measure colors, compositions. We're going to use the high gain antenna on the spacecraft to measure the Doppler shift. So we'll get ideas of the internal structure by measuring the density, and we're going to look for satellites and rings. This is our spacecraft at the upper right. To put this in perspective, the high gain antenna is 2 meters in diameter. The spacecraft from wingtip to wingtip is 50 feet. These things are huge. I'm going to show you some pictures of our solar arrays. Remember, we're actually going further from the sun than any other solar powered spacecraft in history. So we need these really large solar arrays. Our instruments are going to be mounted on this gimbaled, what we call instrument pointing platform that will allow us to point, which is sitting up here. We have 4 scientific instruments on it. We have a high resolution panchromatic imager. We have a wide field panchromatic imager. We have Ralph, for those of you who are familiar with New Horizons, this is actually 2 instruments in one. It's a color camera, and it's a near infrared imaging spectrograph. And then we have a thermal infrared spectrograph on the spacecraft as well. We're covering wavelengths basically from below 4,000 angstroms all the way up to 50 microns. So we're covering about everything that we can. And again, we're going to use the high gain antenna to measure Doppler shifts. So where are we now? This is our schedule that was in actually our CSR. Started working on this back in 2014, actually, where Outlook started in August, and we're somewhere in here. And basically, as of Sunday, all major hardware components have been delivered to Lockheed Martin. Here are our 3 instruments. Again, this is the 2 instruments in one, the color camera and the near infrared spectrograph. Here's our high resolution imager, and this is our thermal infrared spectrograph. There she is. Basically, the entire spacecraft is put together at this point. There, as of Sunday, we put the Ralph onto the what we call instrument pointing platform. So that's now complete. And again, here is our high resolution spectrograph, imager. This is our thermal infrared spectrograph. Here are 2 wide field cameras, and there is our Ralph. So things are really coming along fast. Here's a picture of the solar arrays. They are monstrous. And I don't know if you guys are aware of this. The next one is the coolest picture. These things are actually made out of cloth, right? And they're deployed at like a Japanese fan is deployed, right, after launch. So that is quite cool. So I'm going to finish there and take any questions you might have.
Thank you, Hal. That was amazing. So there is a question for you. Is there any possibility, from Dan Mizanek, is there any possibility of additional encounters in the L5 group besides Patroclus Minucious binary extended mission?
There's nothing close. We had the choice when we designed the mission to look for more targets in the L5 or target Patroclus, right? Because we have that EGA that really gives us a lot of flexibility where to go. Like I said, Patroclus, that binary is particularly interesting, I think, scientifically, so we decided to go for that. And one of the issues with it is it's got a high inclination. So it's actually fairly far out of the plane, right? And that's why we could only target one. So right now there's no other targets within reach. And of course, LSST is coming online, and they're hopefully going to start looking for targets for us. So maybe we'd be able to add something, but we can't promise anything. Also, it's not clear what kind of resources we'll have to be able to go out of our way to find something, but we'll see. We're thinking about it.
Okay, so the next question is by Maurizio Pajola. What will be the maximum spatial scales obtainable on the targets?
Our high resolution imager will get down to 14-meter resolution.
The next question is the same by Paul Abel, talking about the range of spatial resolutions. But yeah, the best is 14.
Well, of course, we can go anywhere from that 14 meters up, right?
Right.
And the area we're going to cover is going to be a function of resolution, right? Because as we get closer, we'll get smaller poster stamps. The observations are designed to be able to give us information of the size frequency distribution of the craters on the surface. So we actually use the model of what we think the crater size distribution is going to be to define particular points in resolution elements we need in size in order to make sure we actually get a good measure of the size distribution of craters.
Okay. And then Peter Jenskins is asking, are there Jupiter family comets that can be reached post-mission?
No, we looked at what, or not that we found, we looked at potential post mission targets, right, for an extended mission at one point, and we found a wide range of things from Hilda's to Jupiter to main belt asteroids. Even Psyche was on the list. Okay, but I don't remember any Jupiter family comets on that list, unfortunately, because that would be really cool.
Yeah. Those are all the questions so far. We have 4 minutes. I'm just going to wait for a couple of more minutes if people have questions. I had a question about just measuring or taking images of Earth during flybys, because you're doing several of them. Is there any plan to do that?
We are certainly, particularly for the first one, developing a calibration plan to calibrate our instruments. I think it's, it's mainly of the moon, actually, right? The problem is that in order for thermal reasons and various other reasons, where the attitude of the spacecraft during the flybys are going to be constrained. So during the actual flyby itself, we're not going to be able to take data because we have to orient the solar arrays in a particular direction. Okay, but on approach, right, we are planning to take some data, at least at EGA1.
Okay. There is another question from Colin Snodgrass. Will the trajectory bring you back to Earth again after the L5 visit to potentially use another gravity assist for an extended mission target?
Yeah, we probably have the option to do that, right? Right now, the targeting is not set up, right? Of course, the perihelion of Lucy will be on an Earth-crossing orbit, right, at the end. But in fact, that's going to repeat for a long period of time. You guys all know me, right? The first thing I did when I got the orbit of the spacecraft was integrate the hell out of it to find out what happens, right? Right, and it spends on average a couple million years basically on the orbit we're leaving it on. Okay, but you know, so we will be coming back on Earth crossing again, but we not trying to make it so that the orbital period of the spacecraft is such that it'll get back to the Earth, so the Earth could be used as an EGA. It's not that we can't do it, it's just we haven't looked into it, right? Our focus is up through the end of that encounter. I should just say, we need to get the best data on the binary. We need to arrive there at a particular relative orbital phase of the binary itself, right, to get to geometry favorable, right? So that's going to set the encounter date more than, you know, getting that orbital period right. Did that answer the question?
I think so. Colin, Colin can probably, yes. Thank you, Hal. This is an excellent.
I
Congratulations.
hope you can all come down to the launch, right? It's
That
really
would be
getting
amazing.
close. You know, if you guys, for the people who haven't worked on missions, like I said, we started this in 2014, right? And it was all paper until about a year and a half ago, right? And now all of a sudden we actually have a spacecraft, right? It's been a wild ride.